So, good afternoon. So today class is about water pinch, water cascade analysis. So, we need to use people use shuttling on stable 5 for you. So, long enough. Based on I think how about that? So for today class, based on this material is it's in any body. It's like number two. Like so PC recovers like two and it's like in this one in case study. So the case study is this one paper. Again, good afternoon. Welcome to our Sunday session. What the pitch analysis. So, what the pitch analysis? There are many method. Last week we have limiting composite curve, what's the cascade analysis, swing and demand curve. But today we're going to learn about what the cascade analysis. So before we start this slide, so I baselining a poll. Mm, So to see your understanding question. So what is the primary bottleneck using the older graphical water surplus diagram or any graphical method like between composite curve for finding the water recovery target. That is okay. We have the what now? So the answer is actually the first one is they can handle multiple contaminant. Uh, Second is yes, they can handle multiple contaminant. Although it's not part of the scope of this class. Highly inaccurate due to calculation error, but that one is not so much calculation because it's a graphical method. But what we learn today, yes, it's a lot of calculation. See the required details trial and error attractive step and find the pinch, which is true. The answer is C. So in order to use limiting composite curve, we need to do some trial and error to find the best. Mm, E is the only word for mass transfer operation. For D, later I this, uh, explain a bit more. So for second slide here, it's actually based on paper by Manan or something. So, um, so, yes. Here's that like, oh, okay. I'm looking at paper by Manan to explain to you about the mass transfer, non-mass transfer equation. This is available indeed as well. Speaking. Uh, so the slide two is based on this paper. I believe this is the best explanation for MTB and M2B. So historically, water pinch was modeled only as a mass transfer process, only for mass transfer. So what is the mass transfer process? Meaning the water is used to absorb the contaminant from another rich stream. But in real chemical and urban system, we feed water as a raw material or blow down from boiler. There are non-mass transfer operation because they do not involve mass transfer between phases. So the advantages of learning WCA or water cascade analysis is actually it can be used to do both mass transfer base and the non-mass transfer base. But for limiting composition, the one that we do the graphical method, that one is limited to mass transfer process. So, so this is a mass transfer base operation. This is for vessel cleaning. This one is for sour gas absorption. For non-mass transfer base, meaning the water will change um, to something else in the some reaction occurs. So the water is lost. This is for the reactor or aniline production. You have input for water, but the output is lower. The same thing for B here. There's no water entering, but after the reaction occurs, ironically is produced with what is the byproduct. So to know more, yes, this is the best people to understand this. Let's transfer this. So I have a rule that so with next my share. So this is the acrylic one. This is based on the Mana 2004 paper that I just showed you. So, for this process, you have ammonia is the main contaminant. So you notice we have a scrubber here. So the scrubber I refer to as a water department. UFW, boiler with water. Also a demand. So to maximize the water reuse in this case, so we should set the limiting chloride and the concentration. Indicator turn to open the 2000. I think paper number 3 or number 2? Yeah, I do. So that I don't have to go get a car. So we understand this one first. So figure 1 show the process flow diagram for acrylic production. AN is produced by the web office among simulation of profiling step factor. Let's say if we dash temperature 450 dBc to 81 according to this equation. So after the reactor, we have hydrogen and water with some gases. Then this one goes to like a cooler. So some of the so that gases condensate. Meanwhile, water go straight to the scrubber. So from the scrubber, we have water. So this water is a wash pit. So after gases to the disposal and So this is a scrubber, so the telemetry is to the indicator, or indicator goes to distillation column, yes, and that is here. Okay. So based on this, you see, all of it, awesome. All of the of-gas condensate, because they will what bottom condensate, everything goes to the wastewater, which is not really economical. So uh, our task is to optimize each one can how to recycle this for stream that goes to the wastewater to return back to the scrap. Scrap. So there are two water demand for this process. The boiler feed water, BFW, and the water feed to the scrubber, the source of water. This is water demand. There are four water source, uh, which include the off-gas condensate here, or the steam jet ejector, the aqueous layer from the decanter, the distillation column bottom, and the condenser of this condensate. Oh, here, this is the steam jet ejector. So we have two demand for water source. In this case, for this in production, the ammonia is the main contaminant. Here, the water source are regarded as wastewater and sent to a biotreatment facility at full capacity. So before we can start, we need to set our target. So to maximize the reuse, instead of getting this water, this forestry goes to the wastewater, we need to recycle back this water, goes back to this. So to allow the maximum recycled wastewater to enter the scrubber, we should set it flow rate index absolutely. So based on this info for scrubber, the wash fit here, It's actually between 5.8 to 6 into and the NHT content or the plastic, you can use pure water or 0 ppm NHT content, or it can also tolerate up to 10 ppm of ammonia content in the washing. So to allow maximum recycled water to enter, we should set the flow it's to a minimum 5.8 kg per second. Allow it contaminated concentration to rise to the absolute upper limit of 10 kg. So, and it's absolute limit is for 10 ppm. Why we need to set to 10 ppm? Because we want to recycle the pure water here. So instead of using pure water, yeah, we redirect this or any of the stream to the water wash filter. Um, so that's why we increased the concentration to 10 ppm. Otherwise, we cannot redirect it if we choose 0 ppm. Um, mm, okay, okay, another poll.
Hello, sir.
Yes.
Gertrude is trying to come into the call. Yeah, there we go.
Already,
Never mind.
yeah,
Yeah,
already, you know, get to
yeah.
Thank you, thank you.
yeah, for it to say that, you know, okay. So the second call to maximize water use, we must establish the limiting water data is a certain demand. Okay. Get it? The maximum allowable precipitation to go force. Okay. So, so that's on the purchases case study for one of the retailers. We for the page 300, so 3,173. It's five. So to have a good targeting tool to determine the true minimum target as a guideline, a good tool should satisfy three basic requirement as follows. So this is talking about which one to choose. Either limited composite curve, sim, uh, WCA, and any other method. The method equal. That one refer back to the first last week slide. So to choose which tool, it must as a guideline certifies three basic requirements. The first one, it should capable of handling both mass transfer base and non-mass transfer base equation. Second, it should consider the flow rate and the concentration variables for the use. And it should be a non-iterative and just completely yield the exact answer. So what we learn today is non-iterative. Sekali buat dapatkan which stream that can be pitched. Return back to the poll. True or false, the answer is true. Minimizing demand flow rate and maximizing its concentration will get expanded. This is talking about Scrabble. Yeah, based on this condition. The lowest flow rate, the highest concentration. Okay. First step in establishing the minimum of the target is to identify it. And minimum, the limiting water data for the process subject to the constraints to the group. So yes, we have the PFD here. but we need to extract the data. So the data of the code is the constraint only the first two that is covered data which will of the stream selected code the use analysis are considered. So ada dua for water use. We need to channel this whole stream going to the wastewater. You can either channel it here, the wash pit, or the scrubber, or the water order. The first constraint may require the flow rate and the concentration of ammonia in the scrubber and the sheet to be bounded within the given range. The one we already covered. By how much? Thus, to maximize water use, one should maximize the ammonia concentration in the flow rate. We want to the second constraint in the only if the water should be used as FW. Why? Okay. If you feel actually limiting okay. So from this statement, the second question is that only pure water should be used as water here. Pure water, only pure water can be used for the toilet based on this condition. This condition is available in the paper. Yeah, with explanation. So since PFW require the content of ammonia is zero, acrylonitrile is zero, so meaning it's it's a pure water. Right. So next is to extract the data. So we have water demand and water source. Water demand in this case only two. We have PFW and scrubber water source. We have four. The solution workup of estimate, this is estimate. The first layer for the detector and the projector on the spin jet detector. Now we learn about water cascade analysis technique. So first we do in the interval water balance. If possible together. First we list our concentration level in ascending order from 0 to 34 ppm. So 0 to 34 point is based on this table, table 1. Presentation is at the last column, 0 until 34. At level 1, what are our demand on source? So at 0 ppm, if you have two, 0 ppm for water demand will be FW, and 0 ppm for the distillation water material. There is no ammonia. Most of the ammonia it goes with ANA, but the condenser, and only some step like ppm, the rest is going to the uh, steam ejector, to condensate goes straight to the reservoir. We have a BFW demand of negative 1.2. So, and distillation word bottom source 0.8. Summing them up. So this is how it look like. So this is level, and this is the concentration from 0 to 34. 1 million, why 1 million? Because of one of the equation later on. This equation. Yes. 1 million is a part per million. That's why it's 1 million. I guess it's 1 million. Mm,
Hi, doctor.
yes.
Sorry, just to let you know, your audio sounds a little muffled and robotic on my end, so it's quite difficult to hear your presentation clearly. I think, can you check on your microphone or audio settings?
Wait.
Yeah, it's a bit muffled.
Okay.
Maybe it's just me. I'm not sure of the rest.
You check for a second.
I think it has a bit. It wasn't a little more now. Even more muffled. I think it has to be your microphone or the mic distance.
Yeah. Testing. Hello, 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 hello.
Hello, sounds better. Maybe.
Okay. Oh, siapa saya dah bersyukur itu? Hmm, si habis lah. Can increase your speaker volume. Yeah.
Can, boleh.
Okay, that's good. That's good to hear. All right, so we continue. Um, okay, we established the first two column here. Column one is level one. That one is okay. So for the second column, this is for based on the concentration that you extracted from the PFT. Next is uh, the calculation start from this column to until habis tu. Oh, okay. Satu-satu. Start from column number, let's say column number 2. Because level is without level can as well, no problem. So for column number 2, each concentration level. So this method is similar to the method presented in this in paper targeting the minimum water flow rate using water cascade analysis technique. If you refer to the textbook, it's good, but it's not new because they made some adjustment. Each of the researcher, they have their own adjustment. Later we see another case study. Slightly different, but the idea is similar. So each concentration level in terms of the water purity in the second column, with the concentration of pure water set 1 million ppm, the fraction of pure water in the contaminated stream or the water purity can be expressed as P equal to 1 million minus C over 1 million. So C here refers to column number 1. So since the first column is, the first row, level 1, is C, sorry, C is equal to 0. So P here automatically 1 point, 1.000 to show that it must be in this, how to say, a significant number. Banyak ni. Ada 6 because the changes occurs at the end. You see, this is 90, this is 86, but before that it's 9999. Yeah, if you bunda bunda dalam bahasa Inggris, just make it 6 significant. Sorry, 6 decimal point. Yeah. And the last one is 0 level 6. That is purity pK. For column 3, delta P. So delta P occurs in between the level. So how to identify? This is just level 1 minus level 2. Sorry, level, yes, so level 1 minus level 2. And so on. So meaning 1 minus 0.99990. Delta P is 0.00001. So column 4. Column 4 and 5 contain the total flow rate for the water demand and water sources at their corresponding purity level. So these two delta sigma ft, sigma fs, refer to demand as a source, refer back to this table. That's on this table. See here, this is demand, this is source. If, so for the water, demand, it's a negative sign. So this is referring to level 1. Only delta P dia di tengah-tengah. Yeah. Tapi is in between purity, pK. So because for concentration at 0, we have 2 value, 1 for demand, 1 for source. For demand is negative 1.2. So for the demand is referring to BFW, boiler feed water. For the water source, refer to distillation bottom. And you expect it as this. So for 10 ppm, only water demand is there. So the scrubber. Why 5.8? Because we set the value just now. Earlier this class.
Why we set this is because of condition for the scrubber. So since source is not, there's no concentration 10 ppm for the source, we leave it blank like this. And next is 5, 6 all for the source. 1525 and 54 ppm. So that's the demand is negative, what the source is positive. So next for column number 6, water cascade tak belum start lagi. This just say we just extract the data to be used for the cascading later on. So FD plus FS. So minus 1.2 plus 0.8. Oh, similar. There is no flow rate for that concentration for water demand. You can leave it blank. Then so column 7, net water source or demand. So negative for demand, positive for source. Yeah. Jambot. Oh. So for this table, the only question that you need to memorize is purity PK. Okay. So how to use 1 million minus C is called. So after we prepare until here, column 6 or 7, now we do the water cascading. So let's do water cascading. So here is a purity level. So we have purity level 1, purity level 5. Yes, level 5. Level, level 6 is the 1 million. Okay, then we have a delta P in between. So 2, 3, 4. Then this is the water cascading. So since we started with, we assume, so for any water cascade analysis, the first thing to do is assume the system doesn't need any fresh water flow rate. Meaning the fresh water fit here is say 0. Then the first value here, negative 0.4, is referring back to the previous table. Column number 6, negative 0.4, negative 5.8, and so on, 1.4. So from here, 1, 2, 3, 1, 2, 3, this 3 column is based on the table that you derived before, that you tabulated before. So for the cascading analysis, it started cumulative from cumulative water source of demand FC. And so the first cascading is here, hence the name cascading, dia macam turun macam tangga. So negative 0.4. So 0 plus negative 0.4, negative 0.4 minus 5.8, 6.2, negative 6.2 plus 5. Ya, macam ni. Follow my cursor, 0 minus 0.4, 0.4, 0.4 minus, because it's a plus, so ini jadi minus. So at the end, this is a wastewater flow rate. So you do the cascading. So the wastewater flow rate is 6.1 kg per second. This is based on 0 fresh water flow. But it's not possible. Any system you need, even though you do the regeneration, later we learn about regeneration, how to reduce the freshwater fit required. But still, you still need freshwater fit. But it's not as much as without the regeneration. Because you see, without regeneration is a lot. Banyak. Continue. And for the pure water surplus or deficit here, so kita buat faham. So for the full water surplus and deficit, actually you multiply the cumulative water source demand or FC with delta P. Ni darab dapatlah value for pure water surplus or deficit. So this column refers to pure water cascade. Also this one, negative 6.2 multiplied with 0.0004 delta P. Delta P refer to purity, not delta P as pressure. Similar to this. And next is doing another water cascading. So this one turun bawah lah, because it's 0. Cascading. Oh, can't explain. The last column here is interval freshwater demand. W, SW equals deficit. It's 1 divided by AXW minus DT. It's 1. So 0.00004 divided by DFW is 1 minus DK1. So jangan apa. Okay. So you see from this now it started to be negative. So product negative value. So to find the pinch, the negative value, we choose the highest, or the largest value of FFWK, the largest negative. The largest negative here is equal to negative 2.057 kg per second. So based on 2.057 kg per second, we choose this value as the freshwater feed. Instead of 0, we choose this value as the feed. And when we do again the cascading, we need to recalculate. We will get the pinch is over here. Should lari tu ya. So next, choose this value as a freshwater feed. So this is 2.057 kg per second minus 0.4, then you have 1.67 minus 5.8, then negative 4 plus 5, and so on. So you see the increasing amount for wastewater because you add fresh water, so some will become a wastewater. At 8.157 kg per second, water will become the wastewater. Then we do calculate the water surplus deficit, and then do the cascading. Do the cascading. And you do the cascading. You see the pinch occur at level 3. This value here actually for the interval freshwater demand is actually negative 2.057. So in terms of the table that you construct earlier, so if we want to include the table as part, if we want to include the cascading analysis as part of the table, is rather than stop at column 6 tadi is, so we add FC. So FC is the cumulative source demand, and then pure water surplus and the cumulative pure water surplus. So 2.06, actually they already how we done this? Rounding. Okay. So for this table, they round it to 2 decimal point. That's why it's recorded here, written as 2.06. Actually, it's a 2.057. So when you do the first table, value for FFW is 0. Yeah. So with this 0, you will see that the cumulative pure water surplus is actually negative here. Tadi lah. But this is only cumulative pure water surplus. We need to identify the interval fresh water demand. Interval fresh water demand, we need to calculate using this equation. So this equation tell you how much fresh water needed. So this value here will be used as the input for the fresh water feed. So meaning you have two tables. The first table is based on FFW equal to 0. The second table, column 1 until 6. Masih cukup. Di tepi saja. So this column from level to FE plus FS is the same. Value dia sama. Later when we cover regeneration, there will be some changes in this part. But for now, stay the same. So meaning you have two separate tables. One FFW equal to 0, another one is FFW with the optimum fresh water needed for this process. Any question? So next is your task is to conduct the WCA. For this exercise, which normally take around pixel easier to calculate this. So I give you 20 minutes including break. Try this one first. Okay. Alright, 2 minutes. Let's start the timer. Any question you can ask to chat. Chat. Try first. we can ini so how much? The pinch. Yeah. We have the frequency. Some pressure. Effective frequency. And then it's 8, 9. Usually the 30.7, 0, 6, 0, 6, 4, 1.3, 33. So you should get okay. One, two, three, 4, 3. So the target for this exercise, 3.592. FFW target. Yeah. 3.592. This one. No, this one is. So meaning the interval freshwater demand is negative 3.592. Kilogram per second. That's a lot. Kan kita buat report. What does negative value in the cumulative figure water cascade? Oh, this point first. Any question for the last WCA? Go to the second case study. Space becomes not remorse. All right. So for this poll, let's see water of higher purity than what is currently available must be supplied. Okay. So water pinch analysis for an urban system, that is University Technology Malaysia. Uh, the urban sector contribute to a significant percentage of water consumption. Maybe in Malaysia, for example, the domestic sector contributes 60% of the consumption to other sectors. The majority of work on urban water conservation is focusing on the design of water saving gadgets, water recycling. The first key step toward minimizing freshwater consumption and wastewater generation is to establish the baseline minimum water consumption target. So this baseline minimum water consumption is what you learned before the previous slide, in which we target for the scrubber, yeah, a certain value. It's 5.8 kilogram per second, which is the lowest. The minimum flow rate coupled with the highest concentration of ammonia, but this one is different. Yeah. Prior to design or retrofit of an urban water network through the notion of water targeting, the description on how the water cascade analysis technique was adapted to establish the minimum water target for the Sultan in most of the WCA technology in Malaysia. See. The first key step toward minimizing, okay, what I do, WCA, okay, so this is the PFT or the water usage, water distribution network for Sultan Ismail Mosque. Is most consume fresh water. Fresh water here refer to the tap water, around 11,550 cubic meter of fresh water annually. A lot. Yeah. So for the fresh water is stored in 4 interconnected distribution tank. So each tank here is gray rectangle, a cube. The volume is 237 meter cube. During the semester, this is the case study. The amount of water consumed for ablution is about 60 meter cube per day on Friday because of the Friday prayer, but only 25 meter cube per day on any other day besides on Friday. In order to estimate the reasonable typical water saving for the most, daily water consumption calculation were based on normal semester day. So they receive how much? 29 tons. So TE is ton equivalent per day is 29.1. Since this is a fresh water, so 0 ppm, no just water, pure water. Then 0.03 goes to the kitchen at 0 ppm. Then the same water after being used, it's 536 ppm. The rest goes to the ton per day, TONNES. Distributed among 4 storage tank, each volume 237 meter cube. So from this 4 tank, the water will be used for ablution, wash basin, shower, mosque cleaning, irrigation, toilet pipe, flushing toilet, and they have this source of not fresh water, but they have rainwater as a in addition to the fresh water. This is at purity of 10 ppm. So all of the water supplied to all of these activities is actually a fresh water, 0 ppm. So the ablution water or rainwater were to be filtered for solid particle like we told that before going through a series of treatment using activated carbon and microfiltration processes. This is a retrofitting designed by IEWRM, referred to the Institute of Environmental Water Resource Management, UTM. So they proposed this idea in which they treated the ablution water goes to the treatment. So this treatment is consists of activated carbon and microfiltration. So they also use redirect the rainwater to be treated using the same system, and this water they recycle back to the tank around 7.27 ton per day at purity 4.2 ppm. This is just retrofitting. They haven't done the water cascade analysis yet. So by doing this regeneration, this design allow an estimated freshwater saving up to 25% with a payback period for investment of about 10 years, which is very long. Oh, it's save up to 25%. Investment about 10 years for payback. So this most case study is a batch process. Since all the water using activity occur in discrete time period. However, in this case, it is possible to use WCA technique developed for a continuous process to establish minimum fresh water consumption in wastewater generation target. The viability of storage and fixed patterns of water utilization allow the MOSCA study to be modeled as a repeated batch process that approaches a continuous system. Oh, so remember the table. It's the same idea, same method. You see? So before you can get this table, you can construct table 6. You need to identify the demand and the source first. So the demand and the source is based on the water distribution network pada Sultan Ismail Elmos. So the water distribution network, the water demand ini dia. So this is based on paper 3, water pitch analysis for an urban system. A case study on the Sultan Ismail Elmos. Okay. So the water demand here, refer back to this figure illustration. So any inlet is the water demand. So here and here. So all of this is the water demand. Water source is after the use. Okay. So normally for water demand. Ini 10 ppm je. So to make this interesting, showing the actual data. So what they do is, that's why you see it here, the reading is 10 ppm. So meaning any water after the storage is not considered as a potable water except for kitchen, because it directly goes from the tap into the kitchen. Yeah. From tap to the kitchen, this is 0 ppm potable water. Then after it goes into the storage tank, although it's fresh water stored in a storage tank, based on the standard, the standard from WCA, based on the paper, water that is transferred to a storage is considered a non-potable water with the minimum BOD level of 10 ppm. Yes, that's why it's set here. BOD concentration is 10 ppm. Otherwise, for the water source after water being used, this is actually according to the actual data in which they do the BOD test to notify this value. Okay. So this table, you get it from the water network. So after we identify the table for water source, water demand, then we can construct table 6, interval water balance for most. So start with the interval level or Previous paper using level, okay, this is using interval n. So since it's interval, so in between, sama. So in between, if you use interval, if you use level, it's actually in line, aligned with this value. So this is interval, then the concentration is ascending order, naik. So based on this data, so we have a lot for 10. Next is the purity Pn using this equation. P equal to 1 million minus C over 1 million. Delta P in between the purity aligned with the interval. And we have a summation for D, summation S, but it's the same, although previous paper using FD, FDFS, but the idea is the same. So negative for demand. So since we have a lot of demand now at 10 ppm, apa ya? Banyak. Yang negatif. Check it. Oh, okay. Negative 0.03 only for the 0 ppm. For 10, you need to add up all of this from 25.03, 22 until the 8. Next is identify the summation S for the source. This one table 2. Yes, we have a value for flow rate 10 ppm. The rest is length. And do this D plus S, demand plus source. Then we identify the net water source for demand, negative for demand, positive for source. So for the cascading, you can either use the table, the interval water balance, or you can do this cascading like this, water cascade diagram. So since this is the first try, so we put we don't know yet how much fresh water needed. So we put 0. Okay. This is the purity K, the delta P, purity difference. The water cascade is based on the summation D plus summation F or demand plus source. Then we arrange it in like a cascade. So delta P is in the interval in between P1 and P2. So this value here, 0.0 T, is aligned with the P1 and P6. Next is doing the cascading. So this is the first cascading to find the cumulative water source or demand FC. So start with 0, get negative 0 minus negative 0.03, you get negative 0.03, then so on. You do the cascading until you obtain the wastewater flow rate 7.67 tons per day. Ton per hour. Should be ton per day. This one. Next is not kosong. Oh. Yeah. Dah silap kita. So for this 15, so for pure water surplus or deficit, actually negative 0.03 multiply with delta P. So here you should get negative 3 times 10 to the power of negative 7. Bukannya kosong. Yes, kosong, but if you round it up, yes, you can get 0. But since this is a lot of decimal point up to 7, 6, so it's 0.000. How many zeros? 6 zeros. Entries. The same thing for this interval. Negative 17.96 multiply with delta P here. And until here. Next is cumulative pure water supply. So you do the cascading again. Yeah, cascading. Next is you find the demand, how much freshwater demand required. So how much water demand required is, let's say this one. Negative 3 times 10 to the power of negative 7, which is the cumulative pure water surplus or deficit from this column, divided by PFW, which is this case 1 minus PK 0.999. Yeah, banyak 9. Duduk 3.5. Boleh ya? This one divided by 1. So PW, because this is a quality of fresh water, which is dia tak berubah. So it's always 1 minus PK. So in this case, in this interval, PK is 0.999. So we go back to this equation. This equation. So this one 3 times negative 7 divided by 1 minus 0.999. How about 10.16 ton per day? So this value is actually calculated by this negative 0.000234 ton per day divided by 1 minus 0.99997. Yeah. Then you get negative 10.16 ton per day. And do the same for the rest. So for interval freshwater demand, here you need to find the largest negative value. So that largest negative value is the target. Target meaning it will turn into pinch. So we target 10.16 ton per day of fresh water. Without any generation, this is the amount of fresh water needed for this system. Yeah. So the pinch occurred here at 23 ppm. 23 ppm refer to equal refer to ablution and wash basin. Yeah, 23 ppm. So ablution banyak, 25 ton per day. Wash basin because it's got this meeting the required concentration. But we can reduce it more, meaning the amount of 10.16 ton per day can be reduced much more. So the initial value required without water cascade, meaning without redirecting the water, is actually 29. Yeah, now we reduce to 10. Okay, we go for regeneration now. So what does it mean? Actually, you can go back to the flowchart. Okay. So after our calculation, these two water can be reused back. years back, any here toilet pipe flushing the toilet maybe. Yeah, it's a lot. 25 plus 14. Kita perlu, yeah. So the amount of fresh water now reduced to 10. How about if we do the regeneration? It can be reduced up to much lower. 4, yeah, 4.2. Yeah. Yes. Okay. Not that the visible water cascade is the one that result in a positive or at least a zero cumulative pure water surplus. In the pure water cascade, the visible water cascade yield the true minimum fresh water FW and wastewater product FW target of 10. Berapa ni pun wastewater tadi? Banyak. Okay, dah berapa wastewater? It should be 29 lah wastewater. Should be 29. So now it reduced to 17 wastewater with only 10 ton per day of fresh water needed. Okay. This is the water cascade table. From the interval water balance, you continue with FC water surplus, cumulative pure water surplus. Next is regeneration. Okay, in order to realize the pinch point and to achieve the maximum water recovery, the portion of the pinch closing source stream, in this case, the ablution and wash basin. Why these two? Because of the pinch occurs at 23 ppm, has to be allocated to a process above the pinch, while the rest to a process below the pinch to limit to design. Referring to the cumulative net water source FC of table 7, out of 25.17 ton per day water source from ablation and irrigation, 7.8 of water found between P2 and P3. P2 and P3 must be sent to region above the pinch. Negative signs indicate sending water across driving cost. Other hand, 17.37 of water found between P3 and P4 must be sent to the region below the P. So to further reduce the water target further, this one, hence water consumption include water regeneration and equipment modification. So for water regeneration, it involves partial or total upgrading of water purity using purification technique. The purification technique, there are many. We have microfiltration, greenhouse filter, sand filter, multimedia filter, biofilter. The regenerated water can either be reused in other water using processes, recycled to the same process to further reduce further water consumption or wastewater regeneration. So the three guide for water regeneration of water source. First point, regeneration above the pinch. So this is the pinch above it. The water source in the region above the pinch are partially treated to upgrade its purity. So water source in this case ada apa banyak? Ada dua aja. Yeah, this one. Satu. 11.13. This is referred to apa tau? 10 repeat kan. Rainwater macam ni. Yeah, rainwater. Mention across the pinch, the sphere. Oh, satu. 25.17. In the region below the pinch, water source in the region below the pinch are partially treated to achieve purity higher than the pinch purity. Okay. So ini region below. So here 0.14 ya. So if you want to treat, ini ya. If you want to treat, because this concentration is 216. So in order to use this water 0.1, 0.14, need to treat it above the pinch purity, higher than the pinch purity, which is 23. Jauh lah. Regeneration below the pinch. Water source in the region below the pinch are partially treated to upgrade its purity. However, resulting water source is still maintained below the pinch. So anything below the pinch, yes, we can treat it, but not up to that pinch value 23, be slightly. But for this pinch, across the pinch, you need to treat berapa? 14, 25, 17. You need to treat it above the pinch. This is a guide lah by this person. So table 7 shows the pinch concentration. Uh, 23 ppm, yes. One possible option of regenerating the water source is to treat the pollution water to a concentration above the pinch. So 25.17 need to treat it above the pinch. Berapa sih pasti? Yeah. But that, how do you know by how much you can reduce. It based on the it's based on the system that you choose. Yeah. Okay. The amount of relation to be treated to 25.17 here. If we go back to the table 1, sorry, table 2, is from the ablution 25.03 tan per day 17 jadi dulu. Hmm, 17. Hmm. Yeah, the amount of emission to be treated depend on the cost of the treatment equipment. An analysis of the relationship between treatment equipment cost and flow rate must be established to know the amount of water needed to be treated that has an appropriate payback period. The total amount of pollution water to be treated using microfiltration is set to 727 ton per day based on statement of the IEWRN case study. Okay. Yes. Refer back to figure 5, retrofitted water never study by IWERN. So after the treatment, in which in this case treatment is repeated carbon plus ultrafiltration. So based on that data, they treated 25.17, ia dapat 7.27 9. Yeah. So they can only treated that much, although the water is much more, but that system produced by this center UTM can only treated this 7.27 ton per day. So, but the concentration is actually improved, since if we choose to treat across the pinch, the concentration must be higher than the pinch concentration 23. So in this case, they can go up to 4.2 ppm. The new water source 7.27. So okay. So from table 9 actually they have done the calculation, but in real world you need to recalculate, meaning set this value. This was what? Set this value to 0 actually. Then we recalculate using a new set of data, 4.2 ppm, 7.27. Recalculate the ability. Now we have a new stream, so interval is 7 now. Okay. Yeah, we have class tomorrow as well, so we can continue tomorrow. Share the attendance first. Kemudian apa kita bincang. Secondary. Your attention. We continue tomorrow. Nak discuss panjang. So tomorrow we'll cover water cascade. We continue first a bit, then we go for gas cascade analysis. That one is much more interesting because a lot of example for regeneration, unlike water cascade. It's just why you need to spend so much for the wastewater. But for gas, yes, you need to do it because inside the gas, the outlet gas or after direction gas, there's still some important expensive gas that you need to recover. Any question? Yeah? Or-
Doctor, do you have the worksheet for the exercise WCA just now? The previous slide,
yes, yes.
the one where we had 30 minutes to do it just now.
Yeah. I upload in Elite later.
Okay, all right. Thank you.
Okay.